This is the grey paper, the Jam grey paper. It's a formal specification in the same rough format as the yellow paper, the thing that I wrote back in 2014. That's the formal specification of Ethereum. I mean, it's been altered by a bunch of people that are not me over the years, but the original document, the original formal spec was mine. Like the yellow paper included the EVM definition, this includes the PVM definition. It's like this is the blueprint for a building. It's not built yet, but this tells you everything you need to know to be able to build that building. In order to make sure that this doesn't describe something that's impossible to build, there is a team. There's actually more than one team at the moment who are building it and making sure that it's reasonable, that it's practical. But the idea is that this blueprint should be reproducible. Other people should be able to build it just from the blueprint. So we want this blueprint to be correct and comprehensive so that we can give this to, the best theoreticians in the world so they can check it and make sure it's good. Make sure it's structurally sound. And check that if it rains, the roof doesn't cave in. And if it blows too much wind, the wall doesn't fall down. This is where publication comes from, because by publishing it, we can allow theorists to start looking at it and picking out problems and hopefully solving those problems as well, but and working out which bits might be better optimized. This has only had a few different sets of eyes on it. It needs more sets of eyes on it, so we want to optimize it further. We want to improve it, and already there are ways that I'm thinking that are already sort of going over how it might be improved. And one particular thing that I want to do is that we're sort of coming to an end game design for. I'm going to be working into this over the next few days. So it's probably going to evolve. The Ethereum yellow paper, this evolved in the same way. After I published the yellow paper, I think in around April 2014, probably I think today, 10 years ago, actually. After I published it, it changed. It changed over 6, 7, 8 months. As auditors looked at it, they picked out problems and they made suggestions for how to improve it and so forth. And we found, but by implementing it, things might change in some ways. I remember logs and receipts changed quite a bit over this period of time. So of course, most people that come to Polkadot know it by parachains. Parachains was the product. It was the original proposition of Polkadot. But in developing Polkadot and making it work, we ended up creating something far more powerful, which was this system for doing a lot of computation and doing it securely in consensus. It's not being fully utilized in many respects. One of those respects was this idea of having one parachain per core. Core is like the term we use for basically a sort of discrete portion of the resources, of this computational resources that Polkadot provides. And really the point of Jam is to be able to use this invention for things other than what Polkadot's original product offering was. This idea of one parachain per core means that parachains that don't really use that much resources end up using or taking up an awful lot of Polkadot's time, when that could really be better used elsewhere, perhaps in some applications that need more but wouldn't pay as much, or perhaps in other parachains that want to use twice as go twice as fast and want to use twice as much of the Polkadot resources cores. This was helped a lot with Agile Core Time, which is this upgrade that's I think it's rolled out now. It's being rolled out, if it's not already rolled out, to Kusama, and it's on its way to being rolled out to Polkadot. And this allows for the possibility of cores to be used other than in a one parachain per core, one core per parachain manner. Unfortunately, it doesn't go as far as I would like. In particular, it doesn't allow cores to do the sorts of tasks that I think would be very interesting to allow them to do. At the moment, the model of a core is still very much based around what it is that a parachain needs. Whereas there we can think already of other things that would still be able to use this underlying resource that Polkadot's generating, secure, resilient computation, but to do so in a slightly different model of usage. And Jam is created to be a reasonably unopinionated general way of providing a model for using this resource. I mean, I actually saw a film only 2 or 3 days ago, the Imitation Game. It's a film about Alan Turing and the creation of this, one of the earliest computers, one of the earliest electric powered ones. Machines up until this point had tended to be built for a particular purpose, and the ability to reuse a machine for many different applications would have been considered a luxury that wasn't worth having. But the ability to reuse the same machinery in different ways allows for levels of innovation that just you can't do if you have to rebuild and reinvent and redesign the machine, this underlying hardware capital, metal and wires and so forth. Every time you think of a new way to use something. And so this idea of a general purpose machine was something that Turing was very excited about. There's even a line in the film about someone sort of jibing with him, saying, "Is this really just a way of you getting the government to fund building your general machine, your universal computer?" That's really what we mean by abstraction. We mean, taking things down from the direct, from the level of direct usage, the level of direct application, to something that's more general that can be used for things other than what we initially might imagine. And this is what allows for innovation. And it's, we see it everywhere in computer science. Abstraction is the first thing they teach on at least my course. It was the first thing they taught. Thinking in general terms, providing other people, or indeed your future self, with the tools that allow you to innovate without the need to reinvent the wheel, rewrite everything from scratch. So finding the right abstraction level is crucial. If it's too low, if you're designing everything to be absolutely as general as possible, then you end up, getting down to the point where you're still having to rewrite everything every time because so little work is done, so little tooling is provided already. Whereas if you set it too high, then it allows you to do a very small number of particular applications well, but once you move beyond this initial design concept, you'll find that it's unapplicable to what you want to do, and then you have to start from scratch. So there's a sweet spot where you're abstracting just the right amount to make what you've done very applicable to a lot of different things, including, one would hope, many things that you've yet to imagine. In some way, I think we're going a little bit backwards, actually. So we started with, and I mean, this has to all be caveated with, I'm not someone who reads blockchain news daily. I'm not someone who keeps up with all the latest trends, all the latest, thought leaders. Stuff gets to me, but usually gets to me through other people. Anyway, the point is I spend most of my time, thinking and coding, and less of my time reading. Now, back when Bitcoin was the thing in like 2012, 2013, the assumption was that the abstraction level was pretty reasonable. Right? You could send Bitcoin, not money, Bitcoin, and there was this scripting language that let you write some kind of interesting, not that interesting in the grand scheme of things, but do some slightly different things with it. You could work out how to make funds that unlocked on certain conditions. You could work out how to do multi-sig schemes where many different people can control a particular amount of funds, and so on. Then Ethereum came along, and it was like, right, we're going to drop the abstraction level down a little bit. We're going to say, or at least that was the proposition, to drop the abstraction level down a little bit. Say, well, we're going to make something. We're going to generalize. Now, in reality, you could question that. You could say, well, didn't really drop the abstraction level down because it added much more to it. In many respects, Ethereum added a lot of features to Bitcoin. It certainly added a lot more instructions in its scripting language, EVM, and it added this concept of gas. It added the concept of storage, and yet it still retained what Bitcoin essentially had, which was balances. So in reality, it kind of added quite a lot. It's questionable whether it really dropped. I would say it didn't. In fact, I would go quite far and say no, it didn't. It did generalize in that it allowed for more things to be done, but it did so at the addition of facilities, at the increasing of complexity. Now, Substrate, I would say, on the other hand, actually did abstract. Right? It said, right, the blockchain won't do anything on its own. It will just execute WebAssembly. Like there is a WebAssembly layer, but it didn't come with any opinion of its own. You could implement Bitcoin on it, or you could implement Ethereum on it, or you could implement basically anything on it. If you wanted a simple sequential blockchain, then Substrate could be used, broadly speaking, for whatever it is that you wanted to do. And we're still seeing new Substrate chains pop up that do like legitimately different things beyond what we would have imagined, what I would have imagined. Now, still, nonetheless, EVM, Ethereum, reasonably general purpose, even if it's questionable whether it was really an abstraction from Bitcoin. Now, the direction that we're really going in now, at least within the Ethereum community, is to really move to make the EVM more of a zero knowledge proof aggregator. So in reality, you're using an increasing amount of these fixed function elements called precompiles in Ethereum language, and you're really only using the EVM to script these precompiles. You're not really doing much work on the EVM itself. In this respect, it's making the main Ethereum EVM chain more of a domain-specific chain. It's reducing the abstraction. It's making it more specific to this application by adding these precompiles and making most of the usage be these precompiles. And I mean, that's not quite the case at the moment, but the suggested future direction, the implied future direction, is to reduce non-zero knowledge proof work, verification work done on this main chain, and instead move all of the interesting business logic out onto other chains that then get verified. In doing this, what they're kind of, you could argue, doing is recreating the Polkadot relay chain, which is very domain specific, specifically for essentially rollups, right? But it provides its own rollup mechanism where it's rolling up the computations done in each of the parachains. That's all very well, but it's definitely moving in the direction of domain specificity and not abstraction. It's moving, if you like, up in the abstraction space closer to this high-level application rather than lowering and becoming more flexible and more general. Whereas with Jam, well, we're already at this Polkadot relay chain situation. And what we're doing is we're actually moving down the abstraction spectrum, and we are increasing the generality, reducing the opinionation. And I think this is I'm excited about this. This is something that I think is leads to much more interesting possibilities. And I'm also quite, at the end of the day, there are opinions in Jam. And many of them are, some of them have come from me, many of them don't come from me, many of them just come from how Polkadot relay chain and its security apparatus has been, has been designed and architected by research team and various developers. And that's fine. I think over time we will see that some of these design decisions could be optimized, and we'll see alterations in the Jam protocol. But I think for now, it opens up enough doors that it's worth pushing forward with. It began quite a long time ago. It began with a forum post by Basti, one of the main developers of Polkadot. It was a throwaway forum post of his. It was like a one-liner. And it was in response to, I think, to the Poker VM the initial Poker VM announcement. It was maybe a year or so ago. And he said, well, maybe we can move towards, maybe it was actually core time. It was either the Agile core time or the Poker VM. In any case, I think it was around a year ago. And he said, maybe we could even put some smart contracts directly on the cores, rather than running them through parachains that sit on the cores. Maybe we can just run smart contracts right there in the core. This would be a lot faster. You can only do this if you have metering in the core, which we don't have with WebAssembly. You could also only do it if you could kind of rent a core out a little bit at a time, which we didn't have back then, but we have now with Agile Core Time. So this sort of combination of having Poker VM which is a metering, but a metered, but still very efficient means of running machine code, of running program software, basically. In addition to having Agile Core Time, essentially sort of lets you buy this secure, resilient computation and run software, whatever software that you want on it, in isolation. Not necessarily software that has to move a blockchain forward. Now, this is interesting, but the problem with it, well, there were a number of problems with it. The biggest one was this concept called synchronous composability. Synchronous composability is the idea that two different pieces, logical pieces of a system, can interact with each other with immediacy, right? So it's like kind of having a phone call versus sending an email, right? An email or even a letter, like a pen and paper letter. Sending a letter takes days to arrive. And you've no real guarantee that it, most of the time they arrive eventually, but you know what Royal Mail's like. It's like, maybe it takes a day, maybe it takes 3 days, 4 days, maybe it gets lost somewhere and then eventually turns up a week later. There isn't really this level of certainty and level of, it's a lot harder to collaborate with someone if you're forced to do it over postage, mail, right? You can do it. You can collaborate a bit faster over email, but the fastest way to collaborate is like in person or over the phone, right? Video call. This is much faster if you want to collaborate with someone than faffing around writing emails or letters, because you have that instant feedback. And that's why synchronous composability, or basically allowing these components to interact with immediacy, rather than firing off a message, sleeping for a while, maybe a block, 2 blocks, 10 blocks, 20 blocks, 100 blocks, then waking up when the reply arrives. This isn't the way that you're going to do really. You're not going to be able to build really intricate machines with different components if each component has to wait this indefinite amount of time to interact with another component. And this is the situation that we have at the moment with parachains, right? They can interact with each other, but it's much slower and more expensive than when they interact just inside of themselves. When they're interacting inside of themselves, we call this synchronous composability. If they host many components, like for example Moonbeam with its smart contract, those smart contracts can interact synchronously, right? They can basically send and receive messages as though no time has passed. But as soon as Moonbeam wants to interact with some other parachain, or maybe across a bridge onto like Ethereum or Kusama or whatever, then time will pass. They basically, if they wait for a response, they have to go to sleep, right? They have to sleep on it, and it could take a really long time for the response to come. This makes doing certain applications impossible, and it makes doing other applications a pain in the ass. Now, there are ways of programming that help this, but those ways of programming are not really applicable to this environment for a bunch of technical reasons that I'm not going to get into. So synchronous composability is really, really helpful. But the problem is, if everything is synchronously composable, then it means you have to have everything all in the same place all of the time. And there's a limit to this. It's kind of like, dinosaurs. Is it dinosaurs? Are they cold-blooded? But it's basically at the limit to a cold-blooded creature. It's like they can grow and grow and grow and grow. But eventually you've got this, it's a ratio, right? It's a ratio between the volume of something and its surface area. And as that ratio gets beyond a certain point, that system can't exist anymore. It doesn't work, because basically it takes too long for stuff to get from the surface down into the middle, and for stuff that maybe is in one place to be able to circulate around and get to some other places. It ends up having basically hot bits and cold bits, and the whole biological metastasis breaks down. It stops being a consistent, coherent, living entity. And it's another reason why, like, for example, the biological cell just can't grow to like the size of a person. There have to be many different cells all working kind of in concert, but independently as well. Yeah. So you see this in biology. You'll see it in all kind of information-based systems, which basically means all systems. They can only grow to a certain size and expect coherency and synchronicity. Which means if you want to scale a system beyond this limit, and it's not to say we'll necessarily hit the limit yet, but if you want to scale beyond this limit, you have to break the system down. Now, that's all very well, and this is exactly what we're doing with Polkadot with parachains, and it's what Ethereum's sort of doing with having multiple ZK rollup things. And you'll see a few other examples of this where, the system is being broken down into different discrete subsystems, and those subsystems work nice and quickly, synchronously, coherently in and of themselves, but then it's a pain in the ass if you want to go between subsystems. So what is really helpful is if you can if we accept that a system needs to be broken down, but rather than breaking it down into what I'm calling now persistent partitions or fragments, so which is to say, like a parachain is persistent. The stuff that lives on a parachain lives on the parachain. It lived on the parachain a day ago. It's living on the parachain now, and it's going to live on the parachain a day in the future. It's a persistent fragmentation of the overall state. The smart contracts that exist on a parachain, they can't freely move to other parachains, right? They sit on that parachain. They stay there. Now, there's not many exceptions to that. Now, that maybe in the future there can be some very heavily small printed exceptions to that, but basically that's how persistent fragmentation works, and that's what to date has been how people have broken these systems. How people have thought about the approach to scaling persistent fragmentation. And as I said, this comes with drawbacks. A system, broadly speaking, is fragmented, but it's fragmented at the level of application boundaries, or user boundaries, or geographical boundaries. There are usually boundaries to a system. It's usually not the case that all components of a system want to interact with all other components exactly the same amount all of the time, right? Usually you can say, well, these bits want to interact and those bits want to interact, but they don't need to interact too much between themselves. One could imagine that, for example, if one had the global transacting system, payments in China mostly go between Chinese residents and Chinese companies, and payments in London mostly go between London residents and London companies. And occasionally a Chinese tourist spends some money in London, and there has to be this thing. And so occasionally, a British tourist goes off to Shanghai and spends some money there. But most of the time, there are these boundaries. But what we don't really want to have to get into is predetermining where these boundaries lie. What would be much better is if we had agile partitioning, the ability to partition and change partitions over time. Yeah, the less decisions we make up front, the less chance there are that we made a bad decision and our system is kind of really suboptimal. And so we end up with this desire to be able to mix and match, to choose our partitions, but to do so every instant of time, right? Now, we can't do it literally every, nanosecond, because that, again, is too much shunting stuff around and working out which bits should go where, and logistics, basically. So we have to be sort of practical and pragmatic about it. But it's not unreasonable to say, well, look, every 6 seconds, let's try and reshuffle our partitions, and according to which bits of our overall system need to interact with each other. Yeah. Because maybe sometimes it's like these bits need to act and these bits need to interact, but other times those bits and these bits need to interact. And so it's and if we end up with a position where a lot of the time these three groups need to interact, it could be quite helpful to sort of pair them up, right? And then just interleave. So every third block, a different pair of these three subgroups are interacting, and this allows us to use much more resources at the cost of adding a little bit of latency, right? If it so happens that someone from here wants to interact with someone from here, but it's it's not their turn, they have to wait until it's their turn, so they might have to wait another 6 seconds. But that's generally not such a terrible thing compared to persistent fragmentation, where they always have to wait a minute plus, or a lack of scale, where they just can't fit in the same system, and half of these guys and half of those guys just aren't allowed to interact. And this agile partitioning requires the ability to mix and match different logical components, putting them in the same core. Yeah. So with parachains, you had just one logical component, the parachain. I mean, it could have subcomponents, but they were always in the same logical component, the parachain. And you fit exactly one parachain, exactly one logical component to one core. With Jam, and this is one of the key differences with Jam, you can fit many different logical components and put them in the same core. And this allows you to do this agile partitioning. There are a few other important elements to Jam. One of the other ones is a two-part computation. So Jam allows for essentially the computation to be broken down. It forces, in fact, the computation to be broken down into two discrete sections. One of them is called the refinement section. The other is called the accumulation section. Now, basically, the refinement section is, you can imagine this as a bit like a flower. So flowers have petals, right? So think of something, I don't know, like is it a chrysanthemum that has all of, like, hundreds of petals? Yeah. And they're all like quite thin, right? Yeah. So think of a chrysanthemum. So the data, it's got like 300-400 leaves. So the data comes in at the end of the leaf, right? And it makes its way through the petal. And as it makes its way through the petal, it gets lots of computation can happen. Petals are like computers, right? They take this data, and there's lots of data can come in at the end of the leaf, and lots of computation happens. And then eventually, as it works its way down the petal, it gets into the middle of the flower, right? The bit where, if you can pull the petal out of, it's the bit that it was joining in the flower at, which I'm going to call the center of the flower, right? The data gets into that center, but the center is very, very small. So only a little bit of data can go in compared to the amount of data that was coming in at the edge of the petal. But the data, when it gets into the center, can mix with all of the other data coming from all of the other petals. Up until then, it could only, the data just had itself within that petal to be interacting with. So when it gets into the middle, it can interact with all of the other petals, or rather all of the other petals' data. And then the middle is what keeps track of where things are at, right? Now, that's your basic model of Jam. Jam, join accumulate machine, is basically this accumulation stage. It's a machine that accumulates. Core Jam, collect, refine, join, accumulate, is the whole sort of protocol. So it's this idea that you collect data, like petals sort of collect rain or whatever coming from the outside. Then they refine it. So this data goes through the petal towards the center of the flower, refining this data and distilling it into some concentrated meaning, right? And then in the middle of the flower, all of this distilled data, this concentrated meaning, is collected together, and then it's accumulated. It's all intermingled, and whatever logic needs to happen to combine it into the next flower, the next stage of this flower. Well, that's the Jam chain. That's the join accumulate machine. So it's joining all of this incoming petal data together and accumulating it, which basically means doing the final processing and taking the repercussions and registering it in the machine. So formal specification basically means a description of the protocol that does not have any significant opinionation in it. So it's sort of like a very pure description of the protocol. A pure description of the protocol can't really be done in anything other than a very pure language. So you wouldn't really want to do it in English. You wouldn't want to do it in a machine language. You'd want to do it in a very conceptual language. And as it turns out, maths is a pretty unopinionated language to describe how a protocol should work, because it specifies only correctness rather than being forced to specify how something should be achieved, right? Maths doesn't really allow you to specify how something can be achieved. I mean, you can dance around it, but it's not something that you can, because there is no general maths computer, right? Maths is really a language for specifying what is the correct outcome. Now, of course, if you only describe what is the correct outcome, you can end up making something that is unimplementable. For example, you say the correct outcome of the system is the piece of data which, when hashed cryptographically, results in all zeros, right? Now, that's perfectly specifiable in maths. Nothing problematic about that at all. But it's impossible to implement as far as we know, right? So care has to be taken that when you're specifying correct behavior, it's possible to implement a practical machine that does do that. And normally you have to tie your formal specification to a real implementation so that you can see both you have the correct behavior on the one hand and you have a demonstration that it's practically possible on the other hand. But if you skip the thing that says what correct behavior is, then you end up with all of the stuff, all of these elements of making it work practically on some particular platform, whether it's x86 machine code or Python or Haskell, right? On some platform, not specifying simply what correct behavior is. You can say, well, correct behavior is what this thing does, but then what that thing does may have very particular platform-specific considerations because it needs to actually make it work. It's specifying when you have an implementation, you're specifying how something should be done, not what should be done. And there is a difference between this. To take a simple example, a sort of an analogy, you might see someone cook a meal, right? Now, if you see someone cook a meal 100 times, you're probably going to work out which bits that they do are the important bits and which bit that they're doing are not important, because that changes between the different examples. But if you have simply one example to go off, if someone, I don't know, and maybe that example is you're not able to watch them in person, but it's actually a film of them doing it. And therefore, you've got the opinionation of the filmmaker in addition to the chef. Then you are stuck with not knowing which bits are important and which bits are not important. Yeah? And you end up with, you can end up with a cargo cult forming. Basically, someone reproducing the unimportant bits and missing some of the important bits. It becomes dogmatic, indeed, because you're not specifying what correct behavior is. You're giving an example of something that exhibits correct behavior, one would hope. But from that example, it's not always so easy to determine which bits are correct behavior and which bits are incidental behavior. And now, of course, you can tie, you can say, well, this bit is incidental, this bit is correct, and da-da-da-da-da. And of course, you can try and use an implementation language to express correctness alongside a lot of comments and commentary and an annotation. But ultimately, you're still going to have quite a lot of opinionation, accidental opinionation, unintended opinionation, unknown opinionation. It's still going to be in there. It always is. When it's a person writing it, it always is. But when you use maths, it forces you to be. My opinion is it forces you to be a lot more. It makes it a lot harder to be opinionated, because maths really, really makes it hard to express anything other than correctness. It's still possible, but it's really hard. And especially if you force yourself to put it not merely in maths, but in the simplest, most concise form of maths. So you really limit how much maths you have to play with, how many symbols you want to use, how many formulas you're going to put it in. Again, this reduces the possibility of opinionation, because you're forcing yourself to adhere to this metric, to respect this metric of conciseness. Essentially of reducing the amount of information in what it is that you're presenting. You can't do the same thing when it's implementation, because implementation languages, their form of conciseness, they're made for expressing not correctness, but rather how to do something. If I have a small program in C, probably if I try to compress a program in C, it's probably going to use lots of pointer arithmetic, because C, it turns out, is really expressive for things like pointer arithmetic. If I have a very short program in, I don't know, Intel Pentium MMX machine code, that does a lot of work, then probably it's going to have lots of the CISC instructions that were introduced in the MMX, because this allowed you to do more stuff in a shorter amount of space. Again, in both cases, it's about the designer of the language and their ideals that come through when you're pushing for a very, very short expression. If you force yourself into maths, there wasn't really a designer of maths, right? Maths is really, set theory is really quite a minimal construct for expressing correctness, expressing axioms, right? Axiomatic systems. And so by forcing yourself to be as concise as possible, you are in some way optimizing for the purity and opinion and non-opinionatedness of your work. So yeah, I mean, the vision is at this point is to stop the relay chain and start the jam chain and migrate everything over from the relay chain into the jam chain. Because the thing is, the parachains, what you can look at the relay chain doing is just having an application. It's an application, right? It's the parachains application. Well, that application, that service, parachain service, that Jam can host services. And the cool thing is that Jam can host lots of different services. And we can write a service under Jam that is the parachains service. So we can actually write what it is that Polkadot is doing, the relay chain is doing it right now, as just a service in Jam. And then we can add other services to Jam later that use what Jam provides in different ways. So the thing is, the relay chain needs to combine Like you can look at if you imagine at the moment, each of the relay chain looks also a bit like a flower, right? Each of the petals process a parachain. Okay, they make sure the parachain is like one block of it has been executed correctly. And then you say, well, what's the middle doing then? What's the center of the flower doing? Well, actually, what it's doing is it's aside from recording where the parachain is at, like the parachain's current state, it's also relaying messages between the parachains, hence the relay chain, right? It's also providing this sort of data conduit. And it's also giving messages back again. It's telling the chain which messages it should also be receiving. So it's able to both receive messages from the parachain and tell the parachain which messages it should be looking at. So it does all of this stuff. That's basically what the center of the flower does. But the thing is, that center of the flower is kind of hard coded on the relay chain. I think in principle it would be possible to evolve the relay chain, but I think it would be a sort of death by 1,000 cuts, because it would be a lot of evolution, and every step in this evolution would be breaking, and parachains I think they would tear their hair out with, like, you know, this each of these breaking changes over and over again. So my feeling here is to there's one other reason as well, which is technical debt. There's quite a lot of technical debt on the relay chain now. So initial design decisions that turned out to be maybe not optimal, and you've made changes. But the thing is, those changes are generally required you to implement the thing that there is now in a not so great way, because you had to take account of the fact something else was happening before. And that's really where we're at. We've done, I don't know, 5 years of coding. How long has it been? Started 2018. Yes, six plus years of coding on Polkadot, right? We have a pretty solid idea about how to make these kinds of systems work, and it's different. You didn't have quite the same understanding of how to design these systems at the beginning. And so it makes sense now, with such a substantial change point, I think, to sort of start afresh and start with a slightly different approach. It'll be work to do this tooling and to make it nice and super smooth, but it's a one-off thing. And at the end of the day, if the migration takes 4 hours, and it means that finality suspends for that period, it's not the end of the world. Parachains would still keep going. It's just that they wouldn't be finalized. So anyone who was doing anything of any significant value on the parachain would probably want to actually fully synchronize the parachain, or connect to a synchronized node that they trust for those 4 hours, right? And then after that, it starts getting rejigged by the jam chain, and everything is good again. So yeah, I mean, I think that 4 hours is probably an overestimate. Realistically, it's probably the case that it can be, it could probably be migrated. Like, I mean, I'm going to pick a number out of the air now, 15 minutes. But the point is that it's a one-off thing, and it can be prepared for, and it can, it's a pill that you take once. And when you've taken it, you've cleared yourself a huge amount of technical debt. And there are a few other advantages, one of which is the ability to have a formal specification, which isn't something that we could do if we kept on the current track of using Substrate. I can't make the decision to halt the relay chain and start the jam chain and move everything over. This is a decision that should be taken by the community. And so one of the things that I'll be doing is putting out a proposal for a governance motion that basically doesn't say implement this and deploy it and we're done, but rather says this, as it's described, is a reasonable direction, and we, the Polkadot community, the dot token holder, gathered dot token holders that whose plurality commands governance, we ratify this as the direction we want to go in with Polkadot. And what does that mean concretely? Well, it means allowing the Polkadot Fellowship, or rather bestowing the Polkadot Fellowship with the responsibility to finalize this into a protocol. Bestowing on the Web3 Foundation the clarity that it needs to support and sponsor further development of this, in particular implementation teams. It means bestowing on the fellowship the responsibility to create the service and the migration tooling, this parachain service and the migration tooling that will make Polkadot version 1 or whatever, the relay chain, compatible with Jam. And it means bestowing on the fellowship the responsibility of halting the relay chain and starting the Jam chain, and basically looking after that migration when the time comes, and dictating when that time is. So basically, it's a yep, we're up for Jam, and fellowship, make it happen. In part, it's up to me to convince other people. In part, it's up to me to up to me and for that matter, other people that are working on this broad project to respond to needs and comments and maybe move it in the directions needed, such that it makes most sense for its users.
Will you be voting on it?
Yeah, probably. I mean, I feel pretty strongly that this is a good direction to go in. I mean, if it doesn't get ratified, then it's not the end of the world. I mean, I wouldn't see Jam as something that I wouldn't do. I'm going to do Jam anyway. I think it's sensible. I think it's a sensible thing. I think it opens up a lot of doors that would otherwise be closed. In particular, this semi-coherent is what I'm calling this idea of agile partitioning of the state, semi-coherence of the system. I think it opens up some really incredible doors. I mean, one of the things that I think is some people can get quite excited about is some sort of zero knowledge roll-up host that would basically reuse Jam's data availability system for ZK rollups, and this would provide potentially a path to. I mean, I don't know. I'm not super optimistic about the prospects of ZK rollups as scaling solutions, but it provides for the possibility of ZK rollups becoming efficient enough, performant enough to efficiently scale, to sensibly and at a reasonable cost scale consensus systems. So that's on the one hand. I can imagine services that do storage services, but do so without the need to have blockchain validators. I could imagine many of the things ultimately, maybe not on day one, but ultimately many of the things that we use blockchains for to be able to be done as Jam services, and to do so with much more, a lot easier than it is to develop and deploy a blockchain at present, without having to worry about validators and all sorts of stuff. One of the things that I'm most excited about is Core Play. This idea of putting smart contract code right directly there on the cores. Now, Core Play, I think, brings a number of things other than that in particular, with PokerVM and its sensible memory model, it allows for the possibility, basically, of running regular code on a blockchain. Regular, normal program code that people just write on a blockchain, like C++ programs that do, I don't know, random stuff, regular console applications. Just put it on a blockchain. It allows for that level of performance, but most crucially, it allows for the ability for these programs to be temporarily halted, memory fetched in, pages swapped in and out, with utilizing the distributed availability system. And if my more recent changes to this stand scrutiny, also the ability to basically keep their memory inside of the Jam's distributed availability system. So basically keep this virtual computer's memory that this program, this regular computer program is running in, inside of the Jam distributed availability system, which means there doesn't need to be extra validators. There don't need to be an extra blockchain. There doesn't need to be extra collators. There don't need to be these actors that you somehow have to incentivize to keep your data around and feed it to you and build work packages with it. It would all be manageable from within Jam. Now, this is a little bit beyond what Jam is aiming for at the present, but this is something that I would hope during the evolution period, and perhaps, hopefully, fingers crossed, even in the next few days, it can be built into the Jam paper, and thus make with Jam this really quite well, it would sit on Jam core play, but it would be this really quite general application hosting service in which you could put EVM contracts, but you could also put Rust programs and Ink contracts and whatever else you wanted to do. And they could all interact with parachains. And they could all go via the bridge. Right? Basically, most applications that we currently can imagine blockchain doing, and applications that we currently think would be way too either data I/O intensive or compute intensive, Jam could potentially make a reasonable prospect. Jam. So with Jam, it's really a push towards this original concept that I pushed out in New York in, I think, early 2015 or mid 2015. This world computer, a computer as a sort of unified machine, in this case semi-coherent, that is scalable enough to actually compute significant amounts, like global amounts of transactive computation of data. I mean, some of the numbers that we're talking about here are very big. I mean, I did some back of the envelope calculations, and these come with a very, very, very large pinch of salt, because this will to some degree rely on engineering concerns as well. But I mean, we're looking at, if you look at the amount of Ethereum gas per second, it could be up to, depending on applications, up to about 1 trillion Ethereum gas per second that this, in aggregate, Jam might possibly be able to process. Like, it's at the higher end, but still. Yeah, so that's that. We're looking at maybe up to around, so I'd definitely say 500,000 times the EVM computation performance across Jam, and maybe into the millions. And PVM still has quite a lot of optimizations to go. So I don't feel that it's unreasonable to say into the millions. Now, it's a low bar to cover, just to be clear. No one in Ethereum is pushing the L1 EVM performance as any kind of highly performant machine, right? Everything in Ethereum is about what's being built on L2, doing ZK rollups, the idea that the EVM and L1 probably is only going to be used to verify these rollups. So it's not that this is meant as a comparison to what Ethereum will be, but rather as a useful yardstick over how much better than this one chain and its various use cases Jam is aiming for. That's what Jam is targeting. Now, this sort of millions of times as fast as EVMs compute. I mean, it's not really millions of times as fast. That's probably pushing it because PVM executes over many different cores. But millions of times of the performance of the computational bandwidth is probably better wording there. Now, in addition to that, it's probably not probably, I can say exactly how much. So, I mean, Ethereum has around 78 kilobytes a second of input data, that basically data that it can take from the rest of the world, and that's assuming you don't use it for anything else. Jam, we're looking at around almost a gigabyte per second of data that can be fed in from the rest of the world. So again, it's not quite a million. Is it a million? No, a bit 1K to a gigabyte, wouldn't it? Yeah. So it's not quite a million, but it's in the tens of thousands of times the amount of data that it can bring in. Maybe about 10,000 times the amount of data that it can bring in and use, right? And again, it's like this isn't really a comparison to what I don't necessarily believe that something that is purported to be in the same generation as Jam can't do as well. But I do think Jam is the difference with a lot of these, with these systems that have yet to be built, is that they're based on a lot of theoretical assumptions. Well, Jam, most of this, like the vast majority, is based on what we've built with Polkadot. Like, we're not building much new technology. We're actually repurposing Polkadot and to a large extent just doing basic optimizations on Polkadot. PVM is new, but PVM also is based on a pre-existing technology, RISC-V, and it's already implemented, and it's demonstrably significantly faster than EVM. And it's also reasonably easy to explain why it's faster. It's just much more in line with modern hardware. It's easier to make something go faster if it's already a lot closer to the thing that's going to be executing it. So yeah, I feel we're definitely going to be able to smash through the current performance limitations of blockchain with Jam. The question is, the only question in my mind is, what will be out there when Jam is delivered? And this is why I'm keen to get the ball rolling with this upgrade. Because if this ends up becoming, a sort of, oh, well, we could do this, and then we could do that, and then we could do the other, and then we have a really long time, going around iterating, then, the world will have moved on. And when Jam finally comes out, it may not be quite so, competitive. I think if we really push to get something finalized, if not implemented by the end of the year, then it's gonna blow everything out of the water in terms of performance. So I mean, the first application is of course parachains. And this is why it's very important to continue the evolution of parachains. And there's going to be a bunch of stuff that Jam will facilitate for parachains, removing the need, or the absolute need for benchmarks within parachains. This is like a pain in the ass thing to do. I've written my fair share of benchmarks to be very, very glad that I don't have to write any more. It also introduces the possibility of using Spree. This is the idea of having accords, essentially parachains that have portions of their logic that are non-negotiable, that are that are absolute and enforced outside of the parachain. So, for example, if a parachain has some tokens logic, it might be in the parachain's interest to say, I give up the right to alter this logic, or I give up the right to change this logic without permission from everyone else that's using it. Or without some governance action that is beyond the control of the parachain. This is currently not possible. The only way you could do it is by putting that logic on another parachain, but then that, as we said before, synchronous composability, you lose that. So it's really handy to have the ability to have this logic sit in the same place as the parachain, so it's synchronously composable, but still not under control of the parachain. And that's what accords are, and that's Jam could do accords really very easily. Makes it very much easier to develop accords. So there's a couple of big things in it for parachains. It just makes sense. It makes sense on so many levels. I mean, I discuss some of the design decisions of Jam. I discuss with the researchers in the Web3 Foundation. Some of the stuff, obviously, I discuss with people that have already implemented similar systems on Polkadot to understand better, why those systems were architected in such a particular way, and help me understand which bits are important for Jam and which bits were incidental, were mistakes, were legacy concerns that are no longer important, were misunderstandings. And, it would be lovely to think that all code ever written was exactly as complicated as it needed to be and and exactly correct and didn't include any opinionation. But honestly, it's so far from the truth, it's laughable. And this is why formal specs are important. And it's why I believe it's important for Ethereum. They've moved away from the yellow paper. They were talking about moving away from the yellow paper for some time. Like I remember, I think even at the DevCon 1, there was talk of I think the Haskell implementation was the original. Let's move away from this formal spec. But some people felt that it was worth maintaining, and they continued to maintain it, which is cool. Makes sense to me. I think now they're finally moving to Vitalik's Python implementation as the source of truth. But again, Python's a high-level language. You can probably make a case that it's not a bad candidate, but I think it's still nowhere near as much of a non-opinionated thing as writing it in set theory. That's right. So this is one of the things that the Web3 Foundation is looking to support. Many different implementations. I mean, with Ethereum, we wanted 3 different implementations when the network launched, and it's the same. Looking for the same thing with Jam. 3 viable implementations of this protocol. So it's a bit like suppose you have a recipe for a meal. Right? As long as the recipe is followed exactly by, it can be 3 different chefs, but as long as the recipe is followed exactly, then you're going to end up with meals that should be, they'll be marginally different in some regards, but they should be indiscernible from each other, right? So if I get blindfolded and take you make 3 different, spaghetti bolognese, right? Spaghetti bolognese, spag bol, right? Easy. So you make 3 different spaghetti bologneses, but you follow the recipe exactly. If it's a good recipe and it's unambiguous, so it has to be unambiguous, has to be a good recipe. But if it's a good recipe, unambiguous, then you can get 3 different chefs, and as long as they're cooks, whatever, as long as they follow the recipe correctly, you can put these 3 plates of spaghetti bolognese in front of someone and have them taste, forkfuls of each, and they shouldn't be able to tell the difference of each one, right? There'll be different dishes, but they shouldn't be able to tell the difference in each one. And that's really what it's about. The different implementations of this have been made by different people. They could even use different ingredients, different languages. But as long as they implement this properly, and we have tests to make sure they do implement it properly, conformance tests, as long as they implement it properly, then you shouldn't know which one you're speaking to. If you speak to one of these implementations, you shouldn't know which one you're speaking to, unless it gives it away. But if it wants to not give it away, you shouldn't know who you're speaking to, like what implementation you're speaking to. And this is the thing. It's like because there is a high degree of likelihood that one of these implementations, every implementation is going to have a bug, right? Our assumption is that this doesn't have any bugs because this has been audited so much, right? It's in the open. I'm not going to say very intelligible, but if you can read set theory, if you're a theoretician, this should be fairly intelligible, at least for working out what something should do. It should be unambiguous. If you, in terms of correctness, right? If you take an implementation that properly that implements it but has a bug, it's not likely to be the same bug as in the other implementations. And this means if you have a network with nodes using a good spread of different implementations, even if one of those nodes has a bug and someone attacks it and they manage to make those nodes go down or go wrong or whatever, the other nodes should keep going. And the network as a whole is much, much more resilient. So the Web3 Foundation has funded development of 2 other clients, or 2 other implementations for Polkadot. And one of them is now at a point, I believe, where it can run a Kusama node and make blocks for Kusama, which probably means it can do the same for Polkadot, but they probably just don't want to risk it quite yet without testing it thoroughly on Kusama. So Polkadot's getting there, but it's not. I'm actually not sure where Ethereum is at the moment with its multiple implementations. I mean, back in the day, it had 2 that were viable, and plus Python that was a bit slow. And then I think there were some other implementations that came along, but I think there was a Java implementation that was pretty good. But I don't know where things are as it stands. With Jam, I want to make sure that there are 3 viable implementations, and indeed, that's in the governance proposal. Jam will not launch, like things won't move from Polkadot Relay to Polkadot Jam until there are 3 implementations that are tested, working with this specification. Now, this isn't something that has been invented for blockchain. It's something that happens all the time in safety critical systems engineering. So one of the most obvious ones that I know of is passenger planes, passenger jets. Their control systems are implemented 3 times by 3 different teams working to the same basic specification and conformance test requirements. The teams are, I mean, I don't know if this is I suspect it may even be a legal requirement, but it will certainly be a contractual requirement for them not to interact at all, right? They're not allowed to talk to anyone outside of their team about this implementation, because to do so, they might risk injecting a bug or an issue that another implementation has. And then on the plane, what it does is it has these 3 implementations for the control system that should do all the same, exactly the same thing, right? So when pilot pulls lever, back, put fins down, whatever it is, they should do the same thing. But if one of them does different, it chooses the two that do the same. So it expects only one to have a bug only to be in one at once. It would really fuck things up if two teams chatted to each other, because that makes it more likely that the bug will appear in two. And then, of course, if the bug appears and the machine that's the little computer's a little control computer that just sort of chooses the thing, all its job is just to choose the two things that are the same, right? If they're all the same, it doesn't matter which two they choose. If two of them are the same, one's different, it chooses the two that are the same. If two of them are the same because they have the same bug, then it's going to choose the buggy one, right? So it's really, really, really important that these teams don't collaborate. So Jam will have, like, one of the ways that we'll do this, we obviously can't prevent people from making nodes in Jam that implementations that don't draw upon other implementations, design decisions. But we're going to introduce an incentivization to Jam called the Jam Prize, the Grey Paper Prize. And this is for Jam implementations that are clean room, and that we find, we'll look at the code, and if the fellowship finds that there is no great reason to believe that the author has been looking at other implementations and bringing in those implementations design choices into this implementation, then it will be applicable for the prize. There are ways of doing this. One of them is, looking at the history, the commit history, making sure that the commit history makes sense. People will often go down incorrect paths in the commit history as they misunderstand bits from the spec and then understand it later and understand why the different bits, and then actually rewrite parts of the code. So we would expect to see this kind of behavior. So there's going to basically be judges that judge not only, there'll be tests to judge whether it's conformant with the spec and performant enough to run Polkadot, but there will also be judges that judge whether there are reasons to believe that this was a clean room environment. So clean room just means they just look at the spec and nothing else, or whether it's more of a derivative and they've looked at some other implementation and just translated that implementation into another language. Web3 Foundation is funding the prize fund. It's a fairly substantial fund. It's 10 million DOT. So I think at the moment that's about 70 million US. And it'll be split in certain ways, but it's not really finalized yet. But basically, we'll set it up so lots of different implementations are incentivized, many different languages, and we want to incentivize people that maybe don't. We want to get people onboarded, right? So we want to make sure that while the prize for developing something that is conformant and performant enough to run Polkadot as a validator node is really nice and high, we also want to have smaller prizes to get people just starting to write implementations and getting to the point where they can synchronize a chain and import some blocks. I mean, ideally, I don't think we're going to see a Jam launch by the end of the year, but if we look to Ethereum and the evolution of the yellow paper as a guide, and I think it's not a terrible guide. Ethereum was in development for about 6 months before the design of Ethereum was being mooted for about 6 months before the yellow paper was published. And Jam is about the same. The design of Jam has been mooted for about 6 months, and by about the same number of people as well. I think there may be 3, 4, 5 in Ethereum that were really thinking about implementing this, reading the spec properly, and writing code. And after the yellow paper was published, it was about 5 or 6 months before we landed on something that could be considered, something that looked like what was eventually launched. basically auditing of Ethereum, of the Ethereum protocol, started at the end of the year, end of 2014, early 2015. I think technically it started January 2015. So yeah, around 6 months after the yellow paper was published, 7 months, 8 months, something like that. And it slowed down the incremental changes. Obviously slowed down quite a lot towards the end. So I think we're going to have something roughly by the end of the year that we're happy with. And I would really hope that we can get something even sooner than that. And I would hope to have 2 or 3 implementations kind of following along, and maybe a few other implementations lagging behind a bit, but ready to really speed up once there's a final draft. So I would hope final draft of the grey paper, end of the year. Notwithstanding any audits that happen afterwards and changes that need to be done because of that. And then maybe we aim for a sort of midsummer jam launch next year. I mean, again, I don't want to. I mean, yeah, exactly. That whole migration and launch thing. Maybe that's. Yeah. And this isn't idle speculation. I'm really just basing it off the timeline that Ethereum followed. So the idea with governance is, yeah, relay chain stops, jam chain starts, everything gets migrated over, and then there's dots. The dots are, instead of being but they're still on the parachains, basically. The idea will be that the dots that sit on the relay chain at the moment, or immediately before the jam chain migration, those dots would move into either a sort of relay chain parachain that just copies the balances over, or maybe more likely the asset hub. And then those balances just get added to the asset hub, or possibly the staking chain. That's the other thing. So then the relay chain would just turn into the staking chain. This is yet to be determined, and there are people working on it. Joe Petrovsky is working on this sort of full time. This idea of getting rid of the relay chain and moving all of its functionality into the parachains. The DOT token itself and all the balances would be just moved over, and there'd be no real change, no change in terms of who held what tokens. Now, there is a question of the DOT token economics. And this, I'd say, is a secondary question for governance, but one equally valid and equally interesting to talk about. At the moment, the DOT token economics were basically, largely pie in the sky, 10% issuance year on year, with that issuance being used to pay for a mix of the staking rewards and the treasury funding. There's already a thing, I don't know if the code has been done yet, but there's already accepted RFC to change that so that it's always 2% that goes to the treasury and 8% that goes to staking. I think it's worth having a conversation about whether long term we want something that is more economically stringent. I think there are good reasons to constrain economics and make them hard to alter. And the economics would ultimately, I think, in my imagination anyway, sit on the jam chain. So it would be the jam chain that issues new tokens, or that controls the issuance of tokens. And the jam chain would not be a inherently upgradable chain, right? It's not built with substrate and doesn't have this WASM thing. Now, the services that sit on the jam chain, including all the parachains, are inherently upgradable. So actually, we don't lose much in terms of upgradability from what we have at the moment. But I think it's an interesting proposition to say the economics should not be inherently upgradable. Maybe a hard fork happens and it does change, but that's a harder thing to bring about. It's reasonable to say, right, well, we've been going for a few years now. We have a pretty clear idea about token economics. We have a much better understanding about proof of stake token economics than we did when Polkadot was launched, 3, 4, 5 years ago. Kusama, what's 2019, 5 years ago. Polkadot 2020, 4 years ago. Let's decide and sort of fix something, and that gives a greater level of certainty for future. And certainty is broadly speaking a good thing if it doesn't come at a significant cost of flexibility. And I'm not convinced we need that flexibility at this stage. We haven't changed this 10% issuance for a very long time. Implying, in fact, we haven't changed the economics, really. Apart from this one RFC, we haven't changed the economics at all. Implying to me that we don't need that flexibility. And therefore, I think a degree of certainty may be very helpful, or may not come at a significant cost, I should say, significant opportunity cost. What would it look like? Well, it could look like all sorts. It could just be that it bakes in this 10% a year. I think a more interesting one, though, would be to look towards if we see, I used to think step curves were a silly thing humans did or a silly thing humans did accidentally. I now see step curves, and when I say step curves, I don't know if you know what I mean, but like curves that don't go in a nice curvaceous fashion, but rather look like a staircase. A very good example of a step curve is the tax system, right? It's like you get taxed some amount until you reach this amount, and then you get taxed some amount more until you reach this amount, and then you get taxed some amount more. It looks very much like, if you draw it out on it as a graph, it looks very much like this staircase. Now, I thought up until quite recently, these different thresholds had no hidden value. They were really just people couldn't handle complicated, mathematical formula, right? They had to fall back on if X then Y, if A then B, if N then the very, very basic heuristics rules. I think and so as mathematicians or as people, theoreticians, when we design systems like this, cryptoeconomic systems, we tend to design them with nice mathematical curves in, because they're more tractable. They're more theoretically reasonable. You can reason about them better theoretically. Steps, they're very hard to reason about theoretically, because you have to kind of reason about, you have to transfer this step into all of the theoretical dimensions that you want to analyze it in. Very hard. And so we end up with, I end up thinking to myself, well, actually, maybe it's sensible. One of the notable things about Bitcoin is the step curve, this halvening every 3 years, the Bitcoin issuance rate halves. Now, what's that about? Like, why not just make it on a nice curve? Why have these discrete events? Step. 50%, 25%, 12.5% Bitcoin. Why make it a step? There is a very, very useful thing about a step that I hadn't realized. It is a Schelling point. It's a natural point that humans can use to form agreement. It's not that it forces them into agreement, but it gives them this default point of agreement. And it turns out this can be very useful in economic systems, to have a very default, or in general social systems, to have a very default point of agreement. You don't necessarily want to force it, because forcing it means that it can potentially then be used as a point of attack. But if it's just a default point, it means that people aren't being coerced or forced into doing particular behavior. It's just what they do. If there's no reason not to do it, then it can really help. And steps are Schelling points. As a very simple example, it's like the steps in Bitcoin form Schelling points of market activity. People do more stuff around the time of the step. Now, there are ancillary reasons why they do stuff, but that doesn't explain all of the market activity, right? But those ancillary reasons have knock-on effects, and those knock-on effects, together with the expectation, give people a reason to do an action that they otherwise don't have any reason to do at some point or another point. It creates waves. And it creates consensus, and it creates coherency. And these can all be very useful things. I think overall, it's an interesting question, not one that I'm necessarily convinced on yet, but I think it's an interesting question, and I've been asked it from a few different people, whether it might be sensible to bring in such economic Schelling points like into a Polkadot issuance scheme. If we want to make Polkadot less inflationary, not deflationary, but perhaps disinflationary, so a system whereby the amount of inflation reduces over time, then this would look something like one way that this could look like, one way that this could look, I think is something that I don't know if it got deployed, but it's definitely something that we talked about a lot during the Ethereum days, which was that you take an amount that is some percentage of issuance at some particular point, and you just add that amount every time. So that as an overall percentage, that amount goes down. So you are disinflationary. Your inflation is reducing in terms of the percent, but it's never deflationary. You're never getting to zero. You're just fixing the amount that you're adding to the system. An example of a disinflationary system would be gold mining if all of the mines were discovered and there were only a certain amount of mining equipment in the world. So it's like you can mine, a ton of gold a year, but you will always mine a ton of gold a year, but you'll never mine more than a ton of gold, never mine less than a ton of gold. And if there's 1,000 tons of gold in the world today, then that represents 0.1% inflation of gold, right? But next year, it represents a slightly lower percentage of inflation. It's still the same 1 ton that you're mining. It's just there's more gold in the world that it's being added to. So that's one possibility. There is also the possibility of doing something a little bit more aggressive that would result in Bitcoin-style discontinuities in the issuance curve, which would be something along the lines of state what the maximum amount is. So, for example, I think we're at about 1.5 billion, 1.4 or 5 billion. I haven't looked recently, but roughly this amount in DOT, as far as I recall. Take that amount and let's say double it. So suppose by the time Jam is launched, we're at 1.7 billion. So suppose the time Jam's launched, we're at 1.57 billion, right? Roughly. Just to do 2 decimal places. Then what we do is we double that to get something roughly pi, 3.14-ish, right? And we say that's the total amount, pi billion, that's the total amount that will ever be minted of DOT, right? And then we say, we take what's left, so we subtract from that pi billion the amount that's already been issued. So in the case of Jam, when Jam launches, it'll be like 1.5, let's say 1.57 billion. We subtract it and we end up with about 1.57 billion. And then we divide that by I don't know, let's say 12, 15. And we say, right, for the next year, that's the amount that gets paid out. It so happens that the numbers are such that, let me think, 1.5. Yeah, the numbers are such that if you divide that amount by, if you say 10%, we take 10% of that and we pay that out over the next 12 months, that would mean no reduction in rewards for that first year, right? Now, after that's been paid out, because it's like 1.5, 10% of 1.5 is billion is 150 million, and that's what would have been provided if you just do 10% of the total amount issued, right? Still the same thing. Now, in the following year, you would take 10% of what's left, right? So that would be less than 1.5. That would be 1.3 or something. 1.35-ish, 1.4, something like that. So it'll go down a little bit. And then the year after that, 10% of what's left. And that would go down a little bit. Less than the year before, but like it will go down. It will go down, but it wouldn't go down as much as it went down from the first to the second year. And you do that each year, and it sort of follows a curve like this, except it would be year on year, so it would step each year. This could be interesting. And then you know, if you say, well, 12 months, we don't want a 12 month thing, we want a 9-month thing, or we want a 15-month or an 18-month thing or whatever. That's also possible. You know, you can just fiddle around with the numbers. This model, I think, is kind of an interesting one. It provides a nice, very shallow curve going from the rewards that are happening at the moment into a fixed final amount model that isn't too aggressive. And it's like, if it turns out to be too aggressive, then you do a hard fork and you say, right, well, we're gonna add more. And you can measure this by saying, you know, by validators, and you can have a soft governance edict that says the amount that Polkadot should, you know, be securing things by in terms of fiat should never be less than 100 million, billion, 2 billion, whatever. So you pick a number, you just say, right, the amount at stake should always be at least this in fiat. And if the staking system isn't enough to guarantee that, then it's like we agree ahead of time to a hard fork that would alter it, increase it so that it's more likely to be able to do that.
It's almost got a safety mechanism.
Exactly. Yeah. I think this would be a very interesting possibility. I think as long as there's like this safety mechanism, I don't really see any big downsides. I do see a serious upside, which is that you've got fiscal certainty, right? And you've got this funny shelling point, which might also add a bit of value. I mean, I don't know if it really would, but people like shelling points. Yeah, people like Pi Day, March 14th. People like April the 1st. People like Shrove Tuesday. They like Valentine's Day. People like these specific points.
A formal specification is to underline the fact that Jam is a protocol. It's not a piece of software. If you want to see more about the grey paper, go to greypaper.com.